Okay, Mariia, if it's good for you, I say we go ahead and get started. I'll kick things off if you're good.
Mm-hmm.
Hello, everyone. Thank you very much for joining the first activity for this year's Northwest Quantum Nexus Winter Hackathon. Today, you're attending the virtual workshop number 1. It will be an introduction to Azure Quantum. And we are very happy to have Mariia Mykhailova today as our speaker. And I'd like to go ahead and turn it over to Mariia now. This meeting will be recorded, so if you have any concerns about that, now's your time to leave. Take it away, Mariia. Thank you.
Thank you for the introduction, Matt. Hello, everybody, and welcome to the first of the workshops leading up to the Northwest Quantum Nexus Hackathon. Today, I'm going to show you Azure Quantum, how to use it to run your quantum code on simulators and on quantum hardware. And I think I'll throw in a new tool that we released just a couple months ago, Azure Quantum Resource Estimation Service, that allows you to estimate the resources that are required to run your hardware, your quantum program on hardware, even if it is larger than the current hardware allows. But before that, I need to throw in something to make sure you're listening carefully. So we're trying something new for today's workshop and for tomorrow's workshop as well. We're trying out a raffle among people who will follow along dutifully and run their Azure Quantum jobs. So if you listen carefully and during the workshop or after the workshop, give a try to doing what I showed you and run an Azure Quantum job, fill this form and get a chance to win a Surface 2 headset. And I'm sadly hoping that Matt will show a link to the form in the chat.
Yes, I will put both those links in the chat. Thank you.
Now that hopefully I have your undivided attention, let me spend a little time giving you an overview of the things you can do with Azure Quantum before we jump right into the demos. This is just one slide I'm going to have today. After that, we're going to live dangerously and do demos. So what does quantum software development workflow look like, and what kind of tools we have to support it? Here is a very rough breakdown of the steps you're going to take when you develop your quantum application. The first step is building it. Well, of course, there is a step 0, figuring out the application you want to develop, the problem you want to solve, and the algorithm for solving it. But that one you might do with pen and paper, so it doesn't necessarily have requirements for quantum software to support it. So for the purposes of software development, it starts with writing the actual software. In the Azure Quantum ecosystem, you can use any of the languages that are supported by it, so Q#, Qiskit, and Cirq. And you can do development in pretty much IDE you like. Visual Studio, Visual Studio Code, Jupyter Notebooks, or pretty much any other IDE. You can also use the pre-built libraries that are included in the language of your choice, which is really convenient. I'm not a huge fan of doing things like modular addition or multiplication by hand from scratch every time. Just no thank you. The second step of quantum software development is integrating it with classical software. It is kind of an indisputable fact by now that quantum algorithms are not going to stand in isolation, even though a lot of introductory quantum algorithms look like just quantum algorithms. For example, if you think about Deutsch-Jaws algorithm, Grover search, they consist of largely just the quantum component. But once we get to more complicated algorithms, the quantum component has to be combined with classical. We want to be able to take advantage of all the advances that classical computing has made in the history of its development and augment them with the new quantum capabilities. For the purposes of Azure Quantum, you can use Python with its libraries and .NET ecosystem with the libraries. Is there a question? Doesn't look like that. The third step is testing your software. I'm sure that if you spend any time at all in software development, you know how important it is to test your software. Especially it's important to test it before you deploy it to actual quantum hardware to make sure that it is correct and that any results you get are any unexpected results, I should say, are due to noise and not due to your algorithm implementation being actually incorrect. This means that you want to use both the classical testing techniques and the quantum testing and program evaluation techniques to help you make sure that your algorithm is correct. This is why we use a variety of tools such as simulators, programs that imitate the behavior of quantum devices with different degrees of accuracy or noise, or sometimes they simulate different aspects of quantum device behavior. And also we use the resource estimators to evaluate whether your algorithm is going to fit within the parameters of the specific quantum device, and if it will not, these tools allow us to optimize the algorithms so that they can fit on quantum devices. And finally, once you have developed your algorithm and tested it on your classical computers using the tools we have in Azure Quantum, then you do the last step. You choose the hardware device on which you want to run your algorithm, and you run it. In Azure Quantum, you have access to partner hardware from Quantinuum, IonQ, and Rigetti, and we have QCI and Pasquale coming soon. That's it for the overview. Today, I'm going to spend most of the time in the last two steps, in evaluating your quantum software and looking at how to run it on quantum hardware. And hopefully I will not spoil the challenge we're going to offer at the hackathon too much. I shouldn't. Let's see. So I am not going to walk you through registering for Microsoft Azure or creating Azure Quantum Workspace. Those are steps that might look slightly different for you depending on whether you use a student subscription or a professional one, what kind of resources your organization provides you. The scenario is going to differ a little bit. So I'm going to start assuming that you have already created an Azure account and an Azure Quantum workspace inside it. For me, I have a quantum workspace called Azure Quantum Demo. And here is what it looks like. I'm going to give you an overview of the tools you have in the workspace. You are going to use it to navigate around and to keep track of the jobs you ran in the workspace and of the credits you have. and of course for actually running your code. So the landing page of the Quantum Workspace looks like this. It's going to have the properties of your workspace. Among them, the two you want to keep track of are the resource ID and the location. Those are the parameters you're going to use when connecting to this workspace from your programs, so that you can use the hardware and software targets provided by this workspace. The tools used to work with the providers and the jobs are here under the operations menu. Let's see. In roughly chronological order, the first tool you're going to use is the providers tool. This is the view that shows you the providers that are available in this workspace and what targets you can use of those providers here. You can see that I have, I think, all of them set up. If we look at a specific provider, for example, IonQ, we're going to see 3 targets here. IonQ Simulator is the cloud simulator, the classical software that simulates the behavior of a quantum device, either without noise perfectly or with noise. The 2 other targets, QPU and QPU Aria 1, correspond to IonQ devices that are available in the cloud. Yes?
Excuse me, a little question. Is possible?
Yeah, sure.
Okay. About the region and inside the guide, I select West use too, or I can select other region.
Oh,
Okay, West use. Perfect.
Yeah, so
I select
this is the location. So generally, you select the location that is closest to you. So I'm on the West Coast, so for me it's West US. If you are on the East Coast, there is an East US
for me,
endpoint.
it's West Europe. For me, it's West Europe. That's good to use.
There are locations that are in Europe as well. I don't remember them by heart. When you create the workspace, I believe, then you select the location closest to it. There is a drop-down menu.
Yes.
Thank you.
And,
thank you so much.
And just to add, it's not a hard and fast rule that it has to be the closest. It's just that's usually the best practice, as Mariia suggested. So if you want to select another region that's showing up in your drop-down, you can do that too. Thank you.
And I think Azure Quantum is available across all regions. I don't think we have a limitation, like use this one or don't use this one. Okay, I was at providers. Okay, so IonQ, QPU, and QPU Aria 1 are the targets that correspond to the IonQ devices that are available via Azure Quantum. QPU is the device called Harmony, which has, I believe, 11 qubits, and Aria 1 is the device called Aria, which has 23 qubits. One interesting thing on this view is the average queue time. The simulators and the actual quantum devices behave differently. For a simulator, when you submit a job to it, there is basically a virtual machine spinned up that runs the classical code to process your program and gives you back the result. So those ones require very little wait time, less than 1 minute, it says here. Actual quantum devices are a scarce resource. So there is just one device on the back end processing all the jobs that go to this target. So you can see that the queue time for those devices can be quite significant, and it can vary quite a lot from time to time. You can see that right now the average queue time for Harmony is 8 minutes, and for Aria it's more than 100 hours. I could probably convert it to days, but it would be multiple days. So for the hackathon, we are going to be partnering with IonQ folks to give higher priority to the job submission from the hackathon participants. But generally speaking, for example, if you are taking a class which has homework assignments to run on a quantum device, this is something you have to take into account, that you're not going to get your results from running a job on hardware back immediately. Okay, let's see. The next tab is probably credits and quotas. This tab helps you keep track of the resource that is called credits. When you create your first quantum workspace, you get credits that allow you to run programs on each of our partners' hardware without actually paying cash for it. You get $500 per provider, which allows you to do quite a lot of experimentation with each of the targets. For example, I have been using this workspace for something like 8 months, and you can see that I still used a little over 10% of my credits with Quantinum and 110% actually with IonQ. So you can do a lot of experimentation here for free, and this view allows you to keep track of how many credits you have left. That's probably all I want to say about this view. The next view, we're getting closer to running code. Just one more tab and we will be there. The next tab is job management. This one helps you keep track of the jobs you submitted to different targets and their status. For example, here you can see that recently I've been experimenting with Microsoft Resource Estimator service. And before that, IonQ simulator and QPU. Things that it shows you are things such as the cost, unless you have been using credits, the provider and the target, so that you can see which one this job targeted, and completion time and completion status, of course, failed or succeeded. Job IDs shown here are the main way you keep track of your jobs you have done in the past, and you can use them for retrieving the results of jobs that you have executed some time ago, which can be extremely convenient if you are running a job, for example, that runs for a couple hours or runs for 2 minutes but stays in the queue for several hours. You're not going to have your program just sitting there waiting for the job to complete. Instead, you're going to go have dinner, take a nap, and then get back and fetch your results using job ID. And now, finally, a place to explore examples of how to run code using Azure Quantum and write your own code. Let me give us a little more space to work with. Highly recommend toggle full screen view. When you go to, okay, so the notebooks is effectively an online place where you can run Jupyter notebooks, either Python kernel or C# kernel. Similar to Google Colab in some ways, different in others. A sample gallery the top entry here in Jupyter Notebooks is a collection of examples provided by Azure Quantum that help you get started with exploring Azure Quantum. We will start with Hello World notebooks from this section. Let's see. So I have already piloted a couple of these notebooks, but if it is your first time here, what you're going to do, you're going to choose a language you want to use, C#, Qiskit, or Circ. You're going to use a provider, IonQ probably, because it's going to be an IonQ focused challenge. And you do copy to my notebooks. And if we do this, for example, for Qiskit plus IonQ, it's going to create a notebook that looks like this, Hello World, Qiskit, IonQ. And let's go and take a look at how this notebook looks like. These notebooks are Hello Worlds, which means they use extremely simple quantum programs to show you the steps of writing the code and submitting it to a cloud target. And here are the steps you're going to take if you want to use Qiskit here in Azure Quantum. The first step is going to be connecting to the Azure Quantum Workspace. Here, it uses these parameters that I mentioned when we started talking about the Quantum Workspace, resource ID and location. And it uses them to connect to Workspace. If you copied a notebook from examples, this cell is actually going to be pre-populated for you. Once you have connected to the workspace, you can access these workspace targets. So a natural next step is checking the list of the targets that are available. You're going to see that the targets here are going to be the same ones we have seen at the provider tab. 3 IonQ targets, a number of Quantinum targets, and depending on when you ran this notebook and which other providers you have, may or may not have Rigetti and Microsoft targets. Then the notebook gently introduces you to the IonQ targets. Again, depending on which provider you chose, this section is going to be different, covering the target of the providers that you selected. And to start with, it's always a good idea to use a simulator to run your code. The simulator is fast, the simulator is noiseless, and IonQ simulator is free, which is 3 very compelling reasons to use a simulator before going to hardware. Is there a question? Okay, I take it as a no. The next step, once you have connected to the Azure Quantum Workspace and checked as targets, is to write the actual code. Here is a very simple Qiskit program that creates a circuit with 1 qubit and 1 classical bit, and effectively uses it to prepare a random bit. And you can use a lot of tools of Qiskit here. For example, you can get IntelliSense pop-ups, you can draw the circuits. So it's pretty convenient. Now that you have built your circuit, it's time to submit it to IonQ. The steps you do here is the first step is getting the backend provided by the provider. So one of the backends of this provider. Here is going to be IonQ simulator because we want to run it on simulator before we go to hardware. And then we do backend.run with the circuit providing the number of shots as a parameter. Here I'm printing job ID for reference, which we can use to retrieve the results later. And here, when I ran this notebook, I took the advantage of the fact that simulator runs are very fast. So I used job monitor to monitor the job in real time. And then I used job.result to which you can use to fetch the job results if you have the job object. So if your kernel has already died and you lost the state, then you have to retrieve the job results based on the job ID. But if your kernel is still alive and your job was fast, then you can just use the job object and get its results. And then you can use the plot histogram tool to get the results. And here they are, pretty standard results for a single qubit random number generator, results that are pretty close to 50-50, but not exactly 50-50. Okay, one more neat thing you can do with the tools before you run on hardware is estimating the cost, which can be a very useful tool if you want to make sure that your job is not going to take you over the amount of credits that you have left for this provider, or if you want to plan that you have to do 15 or 20 similar jobs and that all together they are going to fit within your credits limit. Backend .estimate cost functionality allows you to estimate the cost in this case for IonQ providers in dollars. The next steps that you can do is take the exact same code, change the target you're using from IonQ simulator to IonQ QPU or IonQ QPU Area 1 and submit the same code on a QPU. I'm going to show you this in a different notebook, mostly because that's where I have already pulled up the results from running on hardware. But the process is going to look exactly the same. You have a different backend here, and then you can do backend run for the job just the same way as you did for the simulator. That was our hello world with Qiskit. Now let me show you pretty much the same thing with Q#. I'm going to skip Circ. It's going to be very similar to this tool. And if your language of choice is Circ, you can select it in the gallery of the samples. For submitting the Q# job, the steps are going to be exactly the same. Regardless of your language, you have to connect to Azure Quantum to submit a job. And you have to submit a job. There's kind of no way around it. The syntax is going to be slightly different. But again, each hello world shows you the exact syntax you want to use with this language, so you don't have to guess. So, same steps in Q#. There is a different package to import. One thing I want to emphasize is that the notebook we just saw with Qiskit was a Python notebook. The kernel was Python. Here, the kernel is also Python. And Q# is actually a module in Python that you can import, and you can define Q# code in the same notebook as you define the Python code that you can use to process it. So very convenient for combining classical computation and Q# code in the same notebook. So same steps here, connecting to the workspace, checking the targets available in this workspace. And here Yeah, I think I had exactly the same set of targets here when I was executing this. The same information about the different targets of this provider. Building the quantum program is going to look a little different here. We are going to have a code cell annotated with %% %C#. This means that the code in this cell is in C#. And indeed, this code is not Python any longer. You can see that the code consists of opening namespaces and operations. And inside an operation, you can use C# commands such as qubit allocation, gate application, and measurement. But despite the code looking differently, it does the same thing and as the first hello world we have seen. It's a single qubit random number generator. Once we have the code, we do the same thing we did in the previous example. We choose the target, we set it to NQ simulator, and we run the code using C# Azure execute. The slight difference is that in Qiskit syntax, you choose a provider and you run a job on this provider. And the provider is an object in the code. And here you use a command to set a current target, and then the use of that target is implied in all the following commands until you change the target to something different. So the job submission command itself doesn't have the target explicitly in it.
Hey, Mariia.
Mm-hmm.
Sorry to interrupt, but a question in the chat that I couldn't recall the answer to. Qiskit did not show the queue time for targets. Is that only the case with Q# while you're running in the notebook?
I don't remember whether the queue time is something that is returned in the Qiskit interface or whether it's just a matter of the printing code. So in here, if you get the list of targets, the targets have parameter average queue time. I don't remember off the top of my head if there is a similar parameter in the Qiskit interface. Probably. If there is not, you can use the providers tab to see the current average queue time.
Thanks, Mariia.
Okay, so once we submit the job, we go through the same process of waiting for it to complete. Again, since it's a simulator job, it completed pretty much in under a minute. And the results we get here are actually a perfect 50-50. Another slight difference between Qiskit and C# interfaces. If you use IonQ simulator, in C# interface, it's going to give you the perfect distribution of results based on analyzing the probabilities distribution right before the measurement. In Qiskit interface, it is going to use that distribution of probabilities to run a number of experiments and to aggregate those results. So you are going to get a perfect approximation of results using C# interface and a result that is closer to running on hardware using Qiskit interface. This is something that can confuse people at first. In fact, I first paid attention to this behavior when somebody asked me how come they run a random number generator for a single shot and they still get a 50-50% result distribution. Well, this is how you do it. Obviously, you cannot get a 50-50% distribution with a single shot, but if you're running from this interface, it's going to give you the probability distribution rather than the analysis of actual experiment results. Again, same as with Qiskit Q# interface allows you to fetch job results using job ID later. And I think I'm going to be doing it later. And here we can also plot the result histogram. Here I'm using pyplot, which are going to look suspiciously perfect. Oh no, I can't believe I didn't have the results of Q# job here. Okay, let's live dangerously and try to fetch the results of a hardware job in real time without pre-written code. I'm going to regret it so much. So if I want to find the results of running on QPU, I'm going to see if I was clever. Oh, I was clever. Oh, I see. I was clever enough to name my jobs to have QPU in the title, but I don't see a single bit random number here. And if I do it sorting by target, you see that I did all kinds of interesting jobs on IonQ QPU, but not the random number generator. Yeah, I think this can be interesting. Bernstein-Vazirani on a QPU. So I'm going to go. Let me see that the job results are actually here. Yes. So we are going to very softly and very smoothly switch to a different example here, the Bernstein-Vazirani algorithm. And it looks, it's going to use the same steps as the Hello World example. There is going to be %% Q# cells that include quantum code. This time, since the code is slightly more complicated, it's going to use multiple cells. So the oracle for the Bernstein-Vazirani algorithm, just in case you're not familiar, Bernstein-Vazirani algorithm is a primarily educational algorithm that allows to recover a bit string that describes a quantum oracle in a single oracle call. So this is the oracle that is called in the algorithm. Then you can see interesting things in the algorithm in the notebook as it shows you the other tools you can use. For example, you can use a Q# dump machine library function to print the state vector of the simulation at a certain point in an algorithm. The algorithm itself, here is running it on IonQ. So the same thing here, you use Q# Azure Connect to connect to the workspace. You choose the target, you submit the job. Here you see slightly different syntax than we saw in the previous example. Here I'm also passing the parameters to the job, which is very convenient because you don't need to rewrite your quantum code for different jobs. You can just change the parameter to run the solution for different instances of the classical problem. A slightly different syntax for checking the status of the job. Q#.azure.status checks the status of the last job that was submitted in the kernel. So here the status is succeeded, can also be waiting, executing, or failed. And fetching the results using Q#.azure.output using the job ID. So I did this later than I did the status check. So the kernel already didn't have the memory of the last job it executed. So I had to fetch it by the job ID. And then you do the same sequence of steps to submit the job to QPU. So here you target IonQ QPU, so the Harmony device, the small one, and run a job on it. Here you're going to see the status is going to be waiting. For QPU jobs, it takes some time for them to get to the QPU and to actually start executing. So here I also had to fetch the results using a C# Azure output using the job ID. And you can see that here the results are going to be different from what they were when running on a simulator. When running on a simulator, the Bernstein-Bazirani algorithm, it's actually deterministic. So it's going to return to you a single value with 100% probability. But once we run the same thing on a QPU, we see that the correct answer, the one that gave us 100% probability in simulation, is still the most likely one, but now it doesn't have 100% success probability. It gives us approximately 99% success probability. And there are two more results that creep up with very, very small but non-zero probability. Those results come from noise. The bigger your quantum program is, the more gates it uses and the deeper the circuit is. Roughly speaking, the longer it takes to execute. The more the noise is going to accumulate in the results, and the more unexpected results you're going to see. But this particular example is small enough that the noise is very insignificant and it doesn't prevent us from finding the correct answer. Let's see. And that was it for running your quantum programs on hardware. One more thing I want to show you, and we even still have time for this, is the resource estimation tool. The tool that is going to help you figure out what are the parameter, the resources required for your job execution. Okay, I think this is the right notebook. Let's run all cells and see what exciting things will happen. This is a very new tool, so I don't think I've done any live demos with it. Well, the more interesting it is. So the resource estimation tool is another classical tool for processing your quantum programs. But unlike simulators, it doesn't try to execute your program. And by design, your program is supposed to be larger than can be executed on simulators. It can have millions of qubits, and it will still process it successfully. Because it doesn't try to simulate your program. Instead, it goes through the program and keeps tracks of the things it tries to do. Things like qubit allocation and deallocation, gates that it applies, single and multi-qubit gates, measurement it performs. And keeping track of this, it produces you an estimate of the resources that executing your program on hardware would take. Things such as the number of qubits it's going to take. So the number of qubits a hardware device has to have to execute your program successfully. Things such as the depth of your program, the time, roughly speaking, that it will take to execute your program. And it's going to produce you these results under certain assumptions about not just about your program, but also about the properties of the device it's running on. Things such as the error correction scheme used. Things about the T-factories parameters that are employed to support your algorithm. Those kind of very detailed, very low-level parameters of the execution. Let's see what happened here while I was talking. So this tool is also available as a target in Azure Quantum. So the steps are the same. You connect to Azure Quantum service, but this time you target Microsoft Estimator. Since the estimator is a classical service, it usually has 0 queue time as well. Then you're going to define the quantum operation that you're going to use. Again, works for multiple languages. This one is C#. And you submit the job using the same C# Azure execute. It's going to have fewer parameters. For example, you don't need to define the number of shots. Since it's not trying to run an experiment on your program, the number of shots is rather excessive. And we see that the job status is succeeded very fast. And then we print the result. The result is formatted as this, either a JSON or this HTML table, and it has a lot of fields. The top level ones are the number of physical qubits and the runtime. But you see that those qubits, this number of qubits, is the lowest level number, assuming error correction and T-gate factory and all these details. You can see the breakdown into logical algorithmic qubits, the ones before error correction, and the algorithmic depths, again, the depths of the algorithm before error correction and T-factory. A lot of this information is very specialized. So if you are a person who works with error correction and are familiar with a lot of it, it's going to make sense for you. If you're just getting started with quantum computing, possibly not. And you can see the assumptions that this job made when it was executing. So it assumed, for example, for quantum error correction, it assumed surface code with specific parameters. It assumed the duration of a logical cycle, how long it takes to execute one operation. Assumption about the error rate on logical qubits. Really a lot of fascinating topics. This one, pre-layout logical resources, are the highest levels ones. So the logical qubits pre-layout is very close to the number of qubits that were actually allocated in your program. So if you are curious about this tool, you're most welcome to play with it. In the context of the hackathon, this is something that you can use to estimate the resources that your job is going to need before actually running it on hardware. We will be talking a lot more about this and the more specific tools and parameters you can use during the hackathon kickoff on Friday. If any of you are not going to be there at the hackathon in person, I encourage you to explore these tools and the examples in the sample gallery yourself. There is a lot of interesting content there. And with this, I think that was all I wanted to show you today. If there are any questions, go ahead.
If you'd like to ask a question, just use the raise hand icon and that will start the queue for questions. Thanks. Yes, Alan, you can unmute and ask your question, please.
Yes, hello. Can you hear me?
Yeah.
Okay, so I had a question on the jobs that it runs. So we have these notebooks and these examples, and each job that we run, does that count towards the credits, or does that actually, once we begin making our machine and doing all the necessary tasks that we need to do, like, will it then go to our credit that we have in Azure?
There are some things that do not count towards credits. So IonQ Simulator, for example, is free.
Oh, okay. Gotcha.
IonQ QPU submissions count towards credits, yes. Resource Estimator service is also free.
Okay, gotcha. No, thank you so much for that.
To look up which things are built in which way, you can use Azure Quantum documentation. Each provider has a page, something like this, that documents the targets, the limitations of the targets, and the billing for it. Oddly enough, it doesn't say that Quantum Simulator is free. I mean, I know that it is. Oh, Azure Quantum Pricing. Right. This one must be it. So you can see the more detailed pricing schemes in the documentation. Any other questions?
Yes, I see Chase has their hand raised. Chase, can you unmute?
Yeah, thanks, Matt. Hello, my question is, so on that last example that you showed with the estimator, there was some like really extremely high number of qubits that you need to use for your algorithm. So my question is, how would you actually be able to run this on any available hardware?
No.
Oh, okay.
So these results are kind of looking forward. In the long run, we are not going to be using NISQ hardware. NISQ hardware has a lot of challenges about it. One of them is the high error rates. Second one is, of course, the small scale. In the long run, we are going to be looking at systems that allow us to run error correction, so that the error rate is going to be so low, and it's going to be brought even lower using those error correction schemes. So this number is estimated with this long-term thinking in mind. It assumes that things are happening on large scale. It assumes that your device is quietly running error correction underneath your logical program, which is not the case for any of the NISQ devices. With NISQ devices, kind of what you do is what you get. If you're not running error correction yourself, the device is not going to be running it for you. So for the hackathon, I'm going to have more detailed information on which of these parameters are a description of what actually happens in your device. I didn't have it for this workshop yet. So these numbers, so the highest level numbers, the biggest ones, are there to help you think about the scale at which quantum computers have to grow to be able to run those algorithms. So how big the computer has to be to run those algorithms with those assumptions about noise. And you can see from these numbers that there is quite a way to go.
Okay, thank you. That was a very detailed answer. I appreciate it a lot.
Thanks for the question, Chase. I see we have only 3 minutes left. Are there any other questions people have? I want to remind people to take a look at the chat. We've reposted the links to practice what you learned today and submit a job to Azure Quantum. Thank you, Mariia. And if it's easiest just to go ahead and cut and paste those links from the chat before the session ends, then you'll make sure you have them. So appreciate all the responses so far. We've already gotten quite a few responses come in, so that's great to see.
Nice.
We'll assume that they were very good multitaskers, Mariia, and they were paying very close attention while doing that. Last call for questions. Okay, it looks like strange. Queue got messed up for a minute. Just a second here. Ivan, if you have a question, please.
Yes, this one's about the hackathon's logistics. So, well, when I'm running jobs on the actual IonQ's devices for the hackathon, is there going to be some credits for the event itself that are going to be there, or do we have to use our own credits, or how's it going to work?
Yeah, you will be using the credits you get when creating the workspace.
Thanks.
A much less detailed answer this time around.
Okay, I think that looks like Jorge, you have one question?
Yes, thank you so much for the workshop. Very interesting for me. Very easy to execute the instructions. Is very interesting. Thank you. And the additional question is necessary to fill a survey? Yes, about a survey. Is necessary?
Do you mean the form for the raffle?
Yes, I fill it, the form about roughly. With that is enough. Okay.
Yes. If you've completed the form, then
thank you so much. Then thank you. Goodbye.
Thank you. Okay. I think that concludes our session then, Mariia. Oh, thank you for pushing that up. Yes, please do remember to join our second virtual workshop happening the same time tomorrow evening, where Daiwei Zhu from IonQ will be sharing a very interesting session as well, and you'll have another chance to enter the raffle as well. So thank you for that. Mariia, any final thoughts?
That's it. Enjoy the workshop tomorrow, and I hope to see most of you at the hackathon on Friday.
Thank you so much. Hope everyone has a great rest of their day or evening, depending on what time you're in. Thank you.
Have a good one.